Hey everyone, let's check out this example together about RC circuits. In this example, as you can see, there is an RC circuit that has two capacitors. One is 20 microfarad, the other one is connected to it in parallel, 60 microfarad. And these two capacitors are connected in series with 1 kilo ohm battery. As you can see in this circuit, there is a power supply or electromotive force E is equal to 120 volts, and now we closed the circuit. Alright, so before we closed the circuit, both capacitors, at the time we closed the circuit, both capacitors did not have any charge on them. Alright, so let's just have a quick recap of what's going on here. So we have the charges on the capacitors, so both capacitors. As time elapses, so the charges as a function of time, that's in second, they start both charging, and then it plateaus. The capacitors cannot take any charge anymore. And if that was here, I'm going to make it in green, if that was the current that's going through the capacitor, through the circuit, once we close the circuit, the current will be maximum that is going through the circuit, and the current then will die away as the charge on capacitors fill up. So no more charges are flowing into the capacitors, so the current dies down in the circuit. So that's the current in amps. Alright, now the first part of the problem is that what is the current through the resistor a long time after the switch is closed? So a long time after the switch is closed, so the current here actually after a long time becomes zero. So to answer the part A, so part A is zero. So the current after a very long time in the circuit is equal to zero. Of course, we can prove that by the equation. We know we can think of the current, since it starts with a current I0, with the knowing that it's gonna go down with the exponential function. Okay, now what is I0? You should know that I0 is equal to the battery E divided by the resistance, because at the onset of closing the circuit, the capacitors have no charge, so the current that is flowing through the circuit does not think there is capacitors. So the current thinks this does not exist. So there's only what? The resistor and the battery. So that's the initial current, which is the voltage divided by the resistor. Okay? So I becomes E over R, e to minus t over RC. Now to answer part A again, this will be I'm going to say 120 divided by 1,000 e to minus t. Now t is infinity over RC. So e to minus infinity over RC, this whole thing goes to 0. Okay? Because it's a huge number. 1 over a huge number. 1 over a huge number is 0. And this whole thing is 0. And that's the answer for the first part. So now let's go to the second part. What is the time constant of the circuit? Okay, the time constant, we know that T, tau, is equal to R, the resistor, times the equivalent capacitance. So now the equivalent capacitance, these are two connected on parallel. Since they are both connected on parallel, the equivalent capacitance of them just 20 plus 60 microfarad. So that's 80 microfarad. The resistor is 1 kilo ohm, which is 1,000 ohm, times 20 plus 60 is, that's 80 I said, so 80 times 10 to minus 6, and the answer should be here equal to 8 times 10 to minus 2 seconds, and that's the time constant for the circuit. Alright, good. Now let's go to part 3. How much charge would be stored in each capacitor after a long time has elapsed? So a long time has elapsed. This means the current in the circuit is equal to 0. Okay. If the current is equal to 0, so the voltage drop across here is also 0. So the voltage here across this one is equal to 0. If the voltage here across this one is equal to 0, then this part of the circuit becomes on parallel with the what? With the voltage or the battery. So the voltage across each one of them is 120 volts. So this is 120 volt and this is 120 volt, the same as the voltage of the battery, because they are all on parallel or in parallel. All right, so after a long time, if I want to find the charge on this one, well, the charge, I'm going to call this 1, I'm going to call this 2, so I'm going to call Q1 after a long time is equal to C1 times V1, and that makes sense. Now C1 is 20 microfarads, so 20 times 10 to minus 6, and the voltage is 120. All right, so 2.4 times 10 to minus 3, and that's in coulomb. All right. Now, what is the charge on this one, which is 2? I'm going to take it down a little bit here. So Q2 is equal to C2 times V2. Again, V2 is 120 because it's on parallel. As I said, here's 20, 120. And C2 is equal to 60 microfarad. So this is equal to 60 times 10 to minus 6 microfarad. So 6 times 12 is 72, so that would be 7.2 times 10 to minus 3 coulomb. So that's the charge on each one of them after a very, very long time. So now for part number 4, it asks, determine the total charge on both capacitors, 2 time constants after the switch is closed. 2 time constants. So the time constant, we know that the time constant is equal to RC. So R is 1000, but if you are talking about the capacitor number 1, C for the capacitor number 1 is 20 microfarad. And C for the capacitor number 2 is 60 microfarad. So you need to find the charge, the total charge on both of these capacitors after 2 times constant. You can find the charge on each one of them, then you add the charge. Okay? So the way to do this one is to find the charge. So Q of T equals 2RC is equal to Q0 on each one of them, 1 minus e to minus t over RC. Now this is what? This is the general equation. All right, so if we're looking for the charge on 1, so that would be Q0 for 1, and that would be capacitor number 1. R is the same for both. So that would be Q1 at t equals 2 RC is going to be equal to Q0, 1 minus E. Now T is equal to 2 RC, so that's minus 2 RC divided by RC. And this is 1 and this is 1. Now RC with RC cancels. So we end up basically Q0, 1 minus E to minus 2. And Q0, so Q0 we found it from part number 3, which is the charge after a very long time, which is a maximum charge. So that will be equal to 2.4 times 10 to minus 3. Now 1 minus E, which is, I can write it this way, square. And after some calculation, I can find this charge on Q1 to be equal to 0.002070 coulomb. All right. Now the same way we can find it for Q2. So Q2 at T equals 2 RC is equal to Q0 on the capacitor number 2, 1 minus e to minus t over RC capacitor number 2. Okay, with the same kind of like solution we can find, so we can plug in the numbers for Q0 on charge number 2 after a very long time, which was found in part number 3 to be equal to 7.2 times 10 to minus 3, and this is e to minus 2 ends up, and after some calculation with the calculator we get the number to be equal to Q2 is equal to 0.0622586 coulomb. Notice that this charge on this one is bigger than the charge on this one, almost 3 times, and that makes sense because the capacitor of the capacitance of capacitor number 2 is bigger, and that makes sense now. Okay, so now if you want to find the total charge will be Q1 plus Q2, so add this one and this one, and then you will be able to find the answer to be equal to 8.3 times 10 to minus 3 coulomb. And that's it for this problem. I hope this one solution helped you. Thank you.
It was a good idea.